Testing 1, 2, 3, test. All right, let's go ahead and get going with the midterm exam review. All right, so what I'm going to do is I'm going to go through just some examples of problems. This is not all encompassing of what may show up on your midterm, but it is a good start, and it's definitely something you want to pay close attention to as you are reviewing for the midterm exam. In addition to this, any labs or worksheets or quizzes or lectures or anything like that that we've done in the class, would be important to go back and review those items as well. All right, so here we go. One of the first things you'll see on the midterm is you'll see some basic circuit analysis. So on this example, as an example, one of the things we talked about in here was the Ohm's law, which is E equals I times R, and Watt's law, which is P equals I times E. So it's very important to remember what these components are. So we have volts, we have amps, we have ohms, representing electromotive force is volts. That's why it's an E. I is intensity. That's why it's going to be measured in current or amps. And then resistance is ohms. The only other one that we got to worry about then is the power, which is going to be measured in watts. So in this particular case, this is a simple series circuit is what we're looking at. And as you look at this circuit, the reason why it's a series circuit is there's only one path for current flow. All of the current flow has to go through R2, all of the current has to go through R1, and then all the current goes back to the source. I will always draw current in the electron flow scheme, which is negative to positive, but it doesn't make a difference if you're talking positive, negative, negative, positive. A direct current means it doesn't alternate. It flows in one direction, and in this case, because it's a series circuit, it's going to hit all of these various components. So what you need to be able to do in this class is solve for total current, solve for a current through a component, voltage, wattage, any of that stuff. So let's give you an example here. We know that the total voltage is equal to the total current times the total resistance. That is Ohm's law right up here. And in this case, total voltage is easy to come up with. It's 12 volts. So we take 12 volts, we set that equal to some unknown value of IT, which I don't know right now, but I do know RT. In this case, RT is equal to these two resistances divided, added together. So if I look at those two resistances added together, it's 1150 ohms. So I can calculate RT very accurately, and that is going to be the total resistance of the circuit. So if I divide both sides by 1150, so I divide this side by 1150 and that side by 1150, I will come up with IT equals 12 divided by 1150. I'm typing this in on my calculator. And I'm going to take this out a few decimal points so that we get a good accurate measurement here. 0.01043 amps. Now it's dangerous to show it in this type of notation because, and I'm fine with us showing it in this type of notation. You know, the further decimal places you take it out, the better. In my world, I'd probably prefer to see this as 10.43 milliamps, but I'll be fine with you going out 3 or 4 decimal places to show your work for the total current. So this is one of the things that we're going to that's important for us to be able to solve, is our total current. All right. Now with the total current, the neat thing about total current in a series circuit is the total current is the current through every component. So that 0.01043 amps is flowing through R1 and it's flowing through R2. So it doesn't change. So if I wanted to calculate the voltage of one of these components, it'd be very easy to do. I would say that E of R1, or the voltage of R1, equals the current of R1 times R1. So I'm doing the same exact Ohm's law formula, but now I'm doing it just for R1. So in this case, I don't know the voltage of R1, so I'm going to leave this as my unknown, E of R1. But I do know that I of R1 is the same as the total current, which is the same as R2. So I of R1 is going to be 0.01043 amps, or again, probably milliamps is a better way to justify that, but we'll be okay with this, times R1, which is 680 ohms. All right, so if I take 0.01043 and I multiply that by 680, I get 7.09 volts. So E of R1 equals 7.09 volts. And that is in DC. We know that's in DC because this is a DC source. Okay, so there's E of R1. Now, a neat thing about a series circuit is you can kind of build in a check of your work by calculating E of R2. What I know is Kirchhoff's voltage law says that if I have 12 volts to consume and I only have 2 power devices upon which are going to consume it, then part of it's going to be here and part of it's going to be here. And to be completely honest with you, a smaller piece is going to be here and a larger piece is going to be here because this is a higher resistance, so it's going to consume a higher voltage. You can think of that like a water hose. If I restrict the water hose, if I kink the hose, I'm creating a resistance to flow, and I'm going to have a much higher pressure on the pressure side of the hose than on the downside of the kink. So it's very, very similar to that. But in this case, it's going to be I of R2 times R2. And so E of R2 is going to equal 0.01043 amps. I'm going to multiply that by R2, which is 470 ohms. And I'll do that on my calculator here, 0.01043 times 470. And I get 4.9. E of R2 equals 4.9 volts DC. And now what you're probably going to discover right here is if we add these two together, we don't quite get to 12 volts. So I do have a little bit of a rounding error going on, but it is 11 point something, right? 11.9. Well, I guess it's 11.99. So it's pretty close, right? 7.09 plus 4.9. We get to 11.99 volts. So we don't quite get to the 12, but that goes back to that rounding error. There's probably some decimals beyond the 0.43 here, or the 0.1043 that would get me exactly up to 12 volts. So I feel like we've done something right. The only thing we'd have left to do is if we wanted to calculate power. And again, we could calculate total power, or we could calculate the power of an individual component. I'll do total power first. So the total power is going to be the total current times the total voltage. So E of T. So the total power, total current is 0.01043 amps times the total voltage, which is 12 volts. And if I do that, I get 0.01043 times 12. I get 0.125. 0.125, and I'll take it out a couple of decimal places. 16 watts. Okay, that's the total power consumed by the circuit. Now, again, power is really the ability to do work. When we're talking about a resistor, power might be the heat given off by that resistor. When we're talking about a light bulb at your house, it might be the amount of lamp intensity given by that light bulb. If we're talking about a motor or something, we can equate that to the horsepower of the motor. All right, so let's do one of the components now, P of R1. Now, P of R1 should be less than this, so it's just a gut check because total power would be this power plus this power. This is now going to be the power of just one of the components. So I want to use only IR1 times ER1. So PR1 equals, again, the 0.01043 amps times ER1. We have ER1 from over here at 7.09 volts. So 0.01043 times 7.09 volts. And I get 0.0739, something like this. PR1 goes 0.07395 watts. And the biggest thing you'll screw up on the test, make sure when you're dealing with E, we're talking watts, I, we're talking amps, R, we're talking ohms. Oh, excuse me, E, we're talking volts. Sorry about that. And then P, we're talking watts. So I is always in amps, E is always in volts, P is always in watts, E is in volts, I is in amps, resistance, R is in ohms. So that's important. So hopefully there will be at least 4 or 5 points on your midterm related to a series circuit. So be ready for that. And then obviously we can get into a parallel circuit just the same. Unlike a series circuit, where when you look at the series circuit, the current is forced to go through both components in series, right? A purely series circuit. In a parallel circuit, something different is going to happen. My total current is going to be right here. I'll call this IT. And then part of that total current is going to come up here as IR1. Part of it's going to go over here as IR2. Find my little thing there. There we go, IR2. And part of it's going to go over here as IR3. So what's actually happening is my current is splitting as it's going to these different locations. It's kind of like traffic heading down, you know, I-94, and somebody taking this exit, somebody taking that exit, and somebody taking that exit. What's unique about that, though, is Kirchhoff's current law says that if I take a complete path in a circuit, I have to consume that voltage. So it makes it a little easier, because now what I know is I know VR1 in a purely parallel circuit has to equal 12 volts. Why? Well, Kirchhoff's current law says if I'm an electron flowing this way and I flow up through R1, if that's the only power device I see, then that power device R1 is going to consume a full 12 volts, which means that, guess what? VR2 would do the same thing, and VR3 would do the same thing. So in a purely parallel circuit, those devices are each going to consume 12 volts. And then it's very simple. You know, we do E equals I times R. So, and I got a bad habit here. You see what I'm doing is I'm using V's and E's equivalently. So be very careful about that. That's probably a bad thing for me to do. I'm going to actually go in here and make that a little easier on you by erasing those V's. And I don't remember what I did on the last one. Yeah, I did E of R1, which is much better to keep those consistent. And you can use either one, but I think if I'm bouncing around right now, that's only going to cause confusion. So I'm going to make that ER1, ER2, and ER3. So we're thinking about those as voltage with the Ohm's law E. So if I want to calculate IR1, then IR1 is going to be essentially, if I redo this formula, I equals E over R. So IR1 equals 12 volts divided by 250 ohms. So 12 divided by 250, I get 0.048. The nice thing is that's as far as it goes, so 0.048 amps. If I want to calculate IR2, IR2 is 12 volts again. It's going to be divided by 500 ohms this time. So 12 divided by 500, 0.024, that should make sense to all of us, 0.024 amps. If I want to calculate IR3, this time it's going to be 12 divided by 750. Where's my little cursor? There he is. I need a bigger 12 volts divided by 750 ohms. So 12 divided by 750. I now get a 0.016 amps. And then you got to ask yourself, does that make sense? Well, as resistance goes up and voltage stays the same, current would have to do what? It would have to go down. Now, the interesting thing about this is, what's the total current? Well, the total current is when all of these things come back together, right? So this would be my maximum current, is like what's right here or what's right down here. This would be my total current, right? And what I know is feeding that total current, I've got IR1, which is 0.048 amps, which is coming here, 0.048 amps. I've got IR2, which is 0.024 amps. And I've got IR3, which is 0.016 amps. So all of those are going to feed together to come this total current. So these two are going to combine here as Kirchhoff's current law, and that's going to become a bigger current, right? That's probably going to be 0.24, and 10 is 0.34, 0.4. So I got 0.04 amps coming here from these two, right? So they've combined into this branch. And then these two, the 0.04 and the 0.048, are going to combine up here. And it would look like your IT would then be 0.088 amps. 0.088 amps. So that would be my IT. And you can check that. Good idea to bring a calculator for the midterm, by the way, just so you can check your work. 0.048 plus 0.024. Don't make a silly arithmetic error here. 0.016. I get 0.088 amps. If I then wanted to calculate, let's say, the total power, well, then I know that's IT times ET, right? So the total power, or P of T, equals IT times ET, which P of T then would be equal to 0.088 amps times our total voltage is our source voltage, which is 12 volts. So I multiply this by 12, and I get 1.056 watts. Let me see, 0.088 times 12, 1.056 watts. And for that matter, if you want to calculate any of the individual powers, you do the same thing. You just take P of R1 equals I of R1, but now you just multiply that by not R1, but E1, E of R1. So P of R1 is IR1, which we said IR1 was 0.048 amps. We multiply that by E of R1. Well, each one of these is consuming 12 volts, Kirchhoff's voltage law. So P of R1 is 0.048 times 12, 0.576 watts. So that's the P of R1. So a bunch of calculations there for IR1, IR2, IR3, total power, and then the power of R1. And you could do power of R2, power of R3. But again, a parallel circuit. So again, you could easily imagine getting, a handful. So if we've got 5 questions on series circuits, 5 questions on parallel circuits, I'm not trying to get too advanced on the circuit analysis. Primarily, my goal is to make sure that you understand the basics of Ohm's law and Watt's law, especially as it's going to get applicable to some of the mechatronics and the industrial automation stuff that we're doing in this course. All right, relays. It's very important for you to be able to look at a schematic diagram, whether that's a schematic diagram of a relay on a technical data sheet, or it's the schematic diagram of an elevator control circuit or something like that. And really what I'm looking for when it comes to relays is the ability to identify some key components. So if I look at this one as example, this is a standard ice cube relay, has a round base on it. And it's got sets of contacts. A coil. It's going to have a set of normally open contacts and a set of normally closed contacts. As you look at this, you're looking for something that identifies the coil. Well, I can see right now that this actually looks like a coiled up piece of wire, doesn't it? This is my coil. So my coil terminals are going to be 7 and 2. My normally open terminals. I'm kind of looking for the pairs, but really what I'm looking, and maybe I'll do it this way. I'll say normally open, normally closed, and common terminals, I'll say. My normally open terminals, this is like a switch right here. And that switch can toggle between here, and it can go up to here, like that. And so the normally open terminal is the terminal that it's not touching. That's going to be the key on that. So the terminal that it's not touching is the normally open terminal. So I can see that that switch is not touching 6. So that's a normally open terminal. But I also can see over on this side, I got another set of contacts. And I can see 3 is another normally open terminal. The normally closed terminal is the one that it is touching. So it is touching this little contact here. So 5 is one of them. And 4 is one of them. And then common means that there's a terminal I can wire up to that's going to allow me to switch between the normally open and normally closed. And that's these common terminals that are common to both the normally open and normally closed contacts. So in this case, it would be 8 and 1. Now, if we go over to this particular relay on the other side over here, A little bit different setup, but it's the exact same idea. Normally open, normally closed, and common. This is kind of your typical, maybe what you'd see on what I'd maybe call a NEMA or a North American electrical diagram. A lot of times you'll see the coil look like a coil. Sometimes in some of the international or the IEC stuff, you might see a coil look like a box. So right off the bat, it's the same circuit. They just gave you a little different circuit for the coil, right? The coil now is 7 and 8. The normally closed, you can see that 5 is the common, right? 5 actually can be switched between 3 and 1. You can see that little boom with the switch there. 5 always goes to there, but this switch goes back and forth between 3 and 1. So my normally opens are 3 and 4. My normally closed are 1 and 2. And my commons are 5 and 6. All right, now a lot of times will ask you a question about, well, what would you read if you put a meter on here? So as an example, if I took a meter right now and I said, okay, I want to measure the resistance between 2 points. So if I wanted to, with a meter, take 2 points and measure the ohms or the resistance. And I'll just do it on the one on the right here. I won't do it on the one on the left, but it would be the exact same idea based upon what points you're measuring. So if I took a meter and I measure the resistance right now with a multimeter between pins 1 and 5, what I would read is I'd read 0 ohms. And the reason why is 1 is connected. In a normal de-energized as drawn state, 1 is being connected to 5 because it's a normally closed contact. By contrast, if I ask you to measure between 4 and 6, 4 is not connected to 6 unless the coil is energized. So again, I'm assuming a de-energized state when I make this measurement. And because so, I would read infinite ohms between 4 and 6. Then I might ask you, well, what would you read between 7 and 8? And I would take a lot of answers here. Sometimes people say, oh, I'll read 100 ohms, or I'll read coil ohms or something like that. You know, I always like for someone to say coil ohms or low ohms. It's not 0 and it's not infinite. Everything else is a switch, but the coil has some resistive value to it. A switch is either going to be 0 or open. Let's try one more that's a little bit different. Let's say pins 5 and 2. So pin 5 is right here, and pin 2 is over here. So 5 is a common, and 2 is a normally closed contact. But it's very important to realize that these contact pairs are isolated from each other. So because they're isolated, they never connect together. So this is going to be infinite ohms from 5 and 2. All right, so I think that's pretty good on the relays. Schematic symbols. This is very important, the schematic symbol stuff. I'm going to move this little thing out of the way here. All right. There's tons of schematic symbols. I'm not going to ask you every schematic symbol under the sun. There may be a couple more that I ask you that aren't on here right now. One of them would be something like this. This would be just a switch or a toggle switch. The other one would be maybe something that would look like this, which I would call a normally open push button. And then another one that would look something like this that would be just drawn from underneath and it'd be connected. This would be a normally closed push button. I think everything you see on here right now is a matter of everything that you could possibly ask on the test. So this is I would call this a normally closed proximity switch. This one is a normally open proximity switch. How do I know that? Well, one is touching and one is not touching. Okay, so proximity switch, when I get close, this one's going to close, and when I get close to this one, it's going to open. Now this one's going to kind of give it away, and I don't think I'll hide these. I might hide these on the test, I don't remember, but this is a normally open float switch. This is a normally closed float switch. And what does that mean to you? Well, imagine this is in a tank of water. As the water rises, the water is going to press this switch to close. So this is normally open when the water is not acting upon it. Similarly here, as the water is rising here, this one is closed, and as I press up, it's going to open when the water presses it up. So normally open and normally close. And very similar with this. This is now a normally open pressure switch, a normally closed pressure switch. So when pressure is overcome, this one will close, and when pressure is overcome, this one will open. This is a normally open temperature switch and a normally closed temperature switch. This is a normally open limit switch and a normally closed limit switch. And now these are some of the timing contacts. You'll have to remember back, but we used some timing relays in this lab. So I'll designate these with the acronyms, but pay attention to what I write here. You can see this is normally open, and you'll see the direction of the arrow. This is normally open, timed to close, NOTC. Drawn normally open, and the action is going to be in the closing direction as signified by that arrow, is it's going to go in the closing direction. This one is normally closed. Okay, I can see it is shown in a closed position, and it's important to pay attention to that action too, right? It's going to be pressed up, so it's normally closed, time to open. This one here is normally open, time to open. So it's drawn as normally open, but look the direction that this is going. It's going in the opening direction. So the idea here is I would energize a coil. This thing would close, and then it would delay to open after it was closed. Versus this one here, I would energize the coil, and it would not close right away. It would delay to close. So kind of an opposite action, but they're both drawn normally open. All right, and then this one down here, if we look at it, it's normally closed, but look at the direction of the action there. It's time to close. So this one here starts off in a normally closed position, energize the coil, it opens up, and it delays to close again. So it's kind of funky symbology there, but the big thing is pay attention to the way it's drawn, normally open, and then pay attention to the action or the arrow. So this is the delay to open. Normally closed, delay to open. Normally open, the action is in the opening direction, so time to open. Normally closed, and then the action actually showing it, pulling it closed, time to close. All right, so relay logic. We can use relays to do a lot of cool things. As we look at these are some funky little truth tables you guys have seen in this class. But the idea of using a relay or a pair of relays or contacts or switches to make some logic out of that. So you imagine if the A contact is off and the B contact is off, that's like saying 0, 0, where 0 equals off and 1 equals on. So if A and B are 0, there's no way I can get an output. I'm trying to get through here, right? And if this is open or off, I can't get through. Even if I close B, if I can't get through A, I still can't get through. Or for that matter, if I close A and now I can get through A, but I don't close B and I leave B open, I can't get through. But if I close both of these, I now can energize my output. So 1 and a 1 gives me a 1. And it should be pretty obvious to see now if I close either one of these. If I close A, I can get through. Or if I close B, I can get through, right? So the only way I'm going to get a 0 output is a 0. But if B is on, I get a 1. Or if A is on, I get a 1. Or if both of them are on, I get a 1. So it's a little bit different. You'll notice if I close A, I'm going to energize the control relay. But notice what happens when I energize the control relay. I open this normally closed contact. So any 1 up here, if this goes 1, the output turns off. What I need here is I need the coil to be off in order for this to be on. Because if this coil energizes, that contact's going to open. So if I have a 1 on A, that coil's on, the output's off. If I have a 1 on B, that coil's going to turn on and open that contact. If I have both of these as 1s, the coil's going to turn on and open that contact. The only way I get an output is if I leave both of them off. I think this one's going to be very similar here. Think of this, if I turn on A, this is going to go to the opposite state of, so it's drawn in the de-energized state. So the energized state is going to be opposite. So if A turns on, then this turns off, and I can't get through here, but I can still get through B. If B turns on and I don't turn A on, I can still get through A. So a 0 and a 0, I get an output, right? Because these are both off and they're shown in the de-energized state, so I can get through, right? Or if either one of them, if A is off, I get a 1, or if B is off, I get a 1. The only way I don't get a 1 is if I energize A, then this opens. And if I energize B, then this opens. And now I no longer can get through. And so I have a 0 output. This guy here, kind of a funky guy. This is in series. This one was in parallel up here. But the only way I'm going to be able to energize this coil is by turning both of these on. This on and this on. If I leave either one of them off, the coil will not energize. So this would be a 1, a 1, a 1. If I turn this on and I turn this on, then all of a sudden this coil energizes, this opens, and then the output would turn off. Interesting to look that these two are the same logic. Then the last one here, similar to the one back here, but now we're drawn in series. So drawn in the de-energized state again, a 0 and a 0 is definitely going to give me a 1. But if I turn B on, this opens. So now I can't get an output. Or if I turn A on, then this opens and I can't get through this one. And obviously if I turn them both on, I can't get through anywhere. All right. Moving on a little bit further. Big thing on the I/O listing sheets and with relay logic. You can go back and look at, what's the coil. The coil was 7 and 8, and a normally open was, 3 and 5 or something like that. So you could actually label these, 7 and 8, and 7 and 8 on control relay 2, and 3 and 5, and 3 and 5. So be prepared to do something like that. Big thing on the I/O listing sheet that I'm going to ding you on. When I give you an I/O listing sheet on the test, every block needs to be filled out. Everything. I'm not necessarily looking for it to be perfect. I want you to relabel the rails with the voltage that you're working with. I want an input comment anytime you're connecting to the power, and an output comment anytime you're connecting to the rail over here. And that's very important to show what these input devices are. In this particular case, we would call this, I don't know, what would we call this? If I say S1, switch 2, and then if I want to know what the status of the green lamp is, we could even do this as a relay logic like we did before. If I get 0 and 0, if both of these are off as they're drawn right now, both these coils are de-energized, then these are in the de-energized position, the green lamp is off. If I turn on 1, but not 2, then this coil energizes, and this would go on, but I still can't get through CR2, so the green lamp's off. How about if I go 0, 1? Well, now all of a sudden switch 2 is on, and I might be able to energize this coil, right, by turning switch 2 on. But this coil's off, so now maybe I can get through here, but no longer can get through CR1, so this is off. The only way I'm going to get through is a 1 and a 1. So if I turn this on and I turn this on, I energize both the coils, right? Now both of these contacts switch positions, and the green lamp turns on. So big thing on the I/O listing sheet, complete I/O listing sheets and the ability to analyze, I forgot to put a 1 there, the ability to analyze that I/O listing sheet. A little bit more on the I/O listing sheet. As you look at this, what do we got here? So, I might even just ask you to analyze this and give me a little paragraph as to what this circuit does. You'll notice the normally closed stop, which I might actually ask you as well, what color wire. So like this would be a blue wire. This would be a blue wire. You might say, well, where do I change to white with blue stripe? Well, this is essentially my load. So this is where I would go white with a blue stripe then. So don't be surprised if I ask you, what color wire is here? Well, it's going to be blue. What color wire is here? Well, it's going to be white with a blue stripe. So you look at this, another question I might ask you is, what's the purpose of this CR1 contact? Well, the purpose of that is, right now when I hit start, I'm going to energize that coil. I'm going to energize the time delay coil. What you'll notice though is that when I hit start, it's momentary. So if I release start right away, these coils are de-energized right away. However, CR1 is going to close this contact. So when I release this, it holds it. So we call CR1 there a holding contact. That's very important. And if I look at this then, so I press start, I'm going to go through CR1 because CR1 energized, and the time delay contact energized too. And so now CR1 energized. The only thing CR1 did for me is it gave me the holding contact. It's not used anywhere else. But in parallel with that, I energized the time delay coil, which is a normally open time to close. So now this coil's energized and it's ticking away, whatever it's set to, 5 seconds, 1, 1000, 2, 1000, 3, 1000, 4, 1000, 5, 1000. When that happens, this contact's going to close, energize CR2, and so for the first 5 seconds, I had a red lamp from 0 to 5 seconds. Now, beyond 5 seconds, I now have a green lamp because this contact closed and that contact opened. And the only way to reset this then would be to hit this stop push button, which then would allow me to de-energize the time delay contact, CR1, all of that stuff, open it up and reset it back to its initial state. But big things on this: what color wire am I using? What are these different devices? Is that normally open? Is that normally closed? You know, so on and so forth. And how does the circuit generally work? All right, a little bit more for you guys here. The PLC scan cycle, you can all but guarantee you'll see this in the on the test. I think we've all come up with the redo acronym. So it's read inputs, and I have nothing but an expectation that you just have committed this to memory now. Execute program. Diagnostics and communications, and then update outputs. And I might ask you something like, at what point do we know that a module is not working or something like that? And that's probably, or at what point do we receive data from the HMI? Well, that's going to be during that diagnostics and comms phase. The read inputs is when I'm actually looking at those screw terminal inputs. The execute program is when I'm actually going through all of the ladder logic. I'm not actually turning outputs on though. I'm really updating ones and zeros inside the ladder itself. Then I make sure I can talk to my modules. I can communicate with stuff that's out there over Ethernet or RS-232. And this is where I actually update the outputs. So I do a complete scan where I execute the entire program and I map what everything's going to change, but then I update my outputs last after I've done everything. PLC ladder, be prepared to be given a ladder. If I ask you, well, this is a great example, one that we've done many times in here, right? If I were to tell you, I've actuated switch 1, a certain amount of times, and I want to know what the status of the the green and the red lamp is. So you would go through this and you'd say, okay, I've done switch 1 time. Okay, so I click 1 time, the accumulated value is going to go from 0 to 1. Then I'm going to go down here and I see, oh, I'm going to take the accumulated value in the counter and multiply it by 2. So now I've got a 2 coming out of N007. Is N07 greater than 25? No, it's not. So the green lamp should be off. And if you look at this goofy one, what do we know about the red lamp? Is there anything controlling the red lamp? If the PLC is on, the red lamp is on. So the red lamp is a constant on. Then you might go down a little bit further and you might say, okay, well now I'm at 12. So I went up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now I'm at 12. So now this is at 12. So now my My accumulated value is at 12, so I'm going to take my counter accumulated value, which is 12, and multiply it by 2. So that's going to become a 24 now. Is 24 greater than 25? No, it's not. So this is still off, and this is still on. But the ability to trace through there. So at 13 is going to become 26. 26 now is what's in N0070. 26 is greater than 25. So now this is going to turn on. And does the red lamp turn off? No, because the red lamp is directly connected to the power rail, so now I have both of them on. But the ability to quickly analyze, and I know we've worked through a lot of these, and I've tried to trick you or fool you a couple times, and for the most part, you guys, I think I've got it down pretty cold right now. So the ability to analyze a ladder and determine what's going on based upon the inputs that you're receiving. Human-machine interface. Oop, let me go back here. So as you look at this, don't pay attention to this SP0 and SP1 and stuff like that. But know what these things are going to do. Like, what would I call this? This would probably be a set bit. I'd be setting some Boolean bit. This would be a reset. And it's probably going to be a reset to that exact same bit. Meaning if I want to turn the motor on in my PLC, whatever that is, if it's a B003 element 0, and I think we've had to determine this is like 0300000 or something like that. If I just want to turn the motor on, it's that simple, right? The motor, I'm going to set that bit with this button, and it's going to turn on. I'm going to reset that same address or that same bit with this button, and that bit's going to turn off. The motor's going to be on and off. Now these may also need to look at something, but these are lamps. These are lamps. These are not, so where I'm going to write to this bit, these lamps are probably going to read a bit. What that means is in my PLC program, I might also say, okay, I'm going to use, B003 element 0 is on. I'm going to turn the motor on, but I'm also going to turn on B003 element 1. And maybe if B003 element 0 is not on, or if the motor's not on, I guess I could have done as well. Maybe that'll turn on B003 element 2. So then I might read those bits over here, something like a 03000001 and that one might be, yeah, and then a 0, well, that one would probably be a 2 because it's red, and then a 0300001. So if the motor was on, then the green lamp would be on, and if the motor was off, the red lamp would be on, excuse me. And then down here, if I had a timer or something, motor runtime, and you guess this is probably going to go to our T4, whatever our value is, and whatever that accumulated bit is. So we need to know what the accumulated value is. So I'm going to ask you, what would the best thing to tag this be? Or what, would this be a bit lamp, or would this be a set bit? What might this motor runtime be tagged to? And I might give you, a B file, an N file, or a T4 accumulated file. And I think you should be able to figure out, well, that's probably the T4 accumulated file. We don't have it in the PLC code right now, but that would make sense. Machine vision. Lots of things we can talk about here. The biggest things you really need to worry about is, number one, lighting. What is the most important thing in machine vision? It's lighting. Number two is locating the part. If I don't locate the part, I cannot inspect the part. So you'll see right here, these little arrows represent the location of that part. This part has been located. Now, what are they doing in this? Well, it would appear to me they're measuring from an edge to an edge. So this is probably a distance measurement. What else could you do on this? Well, you could probably count the black blobs. Maybe you want to ensure that all these holes got punched or something like that. You could also, if you wanted to do an angle measurement, you could do an angle measurement. You could measure an angle from a surface to a surface. And they don't have to be surfaces that are in alignment, meaning I can use this as my 0 mark and this as my angle mark, and I can determine, that's supposed to be, a 30-degree angle from there or whatever. I can measure that. So there's lots of different things that we need to worry about with vision. But this location of the part and the lighting, you guys have discovered, in the little bit that you've worked with vision, that is going to be the most important element of what you're doing. And with that, I think that's where I'm going to leave it. The plan is, hold on a second here. So to wrap this up, what you can expect is we'll be taking the midterm exam here shortly after spring break. There will be a series of short answers. You should expect about 50 questions on the test. I'm going to grade that out of 100 points, so I'll make each question worth 2 points. In some cases, if you do most everything right, but you get the wrong answer, I'll give you 1 point. If you get everything right, I'll give you both points. So where possible, you should try to show your work because you may get partial credit. If you don't show your work and you get it wrong, then there's no chance of partial credit. Short answers, especially for the calculations. There will definitely be some IO listing sheet work on there. There will be some definitions and identification of components. Think about sensors or IO listing devices like prox switches and push buttons and things like that. You ought to be able to identify all of those, or the terminals on a relay. But again, 50 questions, 2 points a question. You'll have the entire class period to take the test, and then I think you'll do well on this. The other things you can look at, obviously labs or quizzes or worksheets or lecture notes that you have, are all things to continue to look at in preparation for this midterm. So I hope you enjoyed the video, and I hope you'll watch it at least once and perhaps take some notes and come in ready for the midterm. Thanks.